Good morning, students. Today we are going to discuss about Boolean algebra and logic gates. Okay, okay, students. So in last class we discussed logic gates and what are the logic gates, right? Now we are going to discuss briefly about logic gates and Boolean algebra. Okay, students. Okay, right. First, logic gates. What is mean by logic gate, right? So a gate is a digital circuit which operates on one or more signals and produce signal output. Single output, okay? And next, gates are digital circuits because the input and output signals are denoted by either 1 or low. So gates are digital circuits because the input and output signals are denoted by either 1 or 0, right? Now there are three types of gates, basic logic gates. One is AND gate, another one is OR gate, another one is NOT gate. So these are the basic logic gates. Okay, students, right? Now, so in our book, under the title, see this, a logic gate is an electronic circuit which functions based on digital signals, and the logic gates are considered as the basic building blocks of most of the digital systems. It has one output with one or more inputs. There are three types of basic logic gates. One is AND, OR, and NOT. The other logic gates are XOR gate, NAND gate, and NOR. They can be constructed from the basic logic gates. So the XOR gate, NAND gate, NOR gate are constructed from the basic logic gates. Okay, students? Right. Now, so we already discussed, right, the basic logic gates. One is, see this, NOT gate, AND gate, OR gate, NAND gate, NOR gate, and XOR gate. So these are the symbols. Okay, I'll tell you one by one. First gate is NOT gate. First gate is what? NOT gate. See this? The NOT gate is an electronic circuit that gives a high output. That gives a high output if it is input is low. See, the NOT gate is an electronic circuit that gives a high output if its input is low, and NOT gate takes only one input signal and produce only one output signal. At the same time, the output of NOT gate is complement of its input, so it is also called inverter. So see this symbol of NOT gate, only one input and only one output is, so a bar. So a is a Boolean algebra, a bar, yes, a inverse. So if it is input is low, the output is high. Suppose the output is high, the input is high, the output is low. Okay, students, right? And next, AND gate. Which gate? AND gate. See, AND gate. The AND gate is an electronic circuit that gives a high output only if all inputs are high. Okay, if only all inputs are high, and the gates takes two or more input signals. The gate takes two or more input signals and produce only one output signal. So AND gate takes two or more input signal and produce only one output signal. And see the Boolean algebra formula is A dot B. See, this is the symbol of AND gate. Two input, only one output. See, both are low. Inputs are low, the output is low. Is both in one, if any input is low, the output also low, but both the inputs are high, then only it gives the high output. Okay students, right. Next, OR gate. The OR gate is an electronic circuit that gives high output if one or more its inputs are high. And OR gate also takes two or more input signals, and produce only one output signal. Right? And there is the symbol. There are two inputs, only one output. A plus B is the Boolean formula. A plus B. See, in this case, two inputs are low, the output is low. If any input is high, definitely the output is high. Okay students, right. And this is NAND gate. Yes, see, NAND gate. This NAND gate has two inputs, one output, right? Okay, the formula is A dot B the whole bar. A dot B the whole bar in our book is given. See this, if any two inputs are low, it gives the output high. This is 0 1 and 1 1 0 1, but two, see this, two inputs are high, the output is low. That is the inversion of AND gate. The results are inversion of AND gate. Okay students, right. This is NOR gate. NOR gate is that opposite function of what? OR gate. This is the symbol. It has two inputs and only one output. Yes, the formula is A plus B the whole bar. That is inversion of OR gate. That's why, see this, if it is 0 0 0 0, what is 0 0? Two inputs are low, it gives output. If any input is high, definitely it gives the low output. That means 1 plus 1, actually 1 plus 1, A plus B, 1, will take inverse 0. Yes, that's why. So it is a opposite function of OR gate. Which gate? OR gate. Okay students, right. XOR gate. So XOR gate is the exceptional gate. There is a symbol of the exception gate. It has two input, only output. Okay, right. A exclusive B, we called as A exclusive B, right? Yes. Now see, this is that input 0 0, the output is 0. Okay, both inputs are high, the output is low. If any input is high, definitely it gives the high output. Okay students, okay. So NOT gate, AND gate, OR gate, NAND gate, NOR gate, XOR gate. Okay students, right. Now, yes, with the formula, yes, Boolean algebra formula, I'll explain, please then. Yes, with another diagram. See, this is input, this is output. What is that formula? Boolean algebra formula A bar. That is inversion of A, inversion of input. See, input is 0. What is output? A bar. So 1. Input is 1. Output is what? Inverse. Therefore 0. Right? This is which gate? NOT gate. This is the symbol. And next, AND gate. See, AND gate A dot B. What is the formula? A dot B. 2 input, only 1 output. And this is the switching yes diagram. Both yes switches are open. Is there any current flow? There is no output. That's why both are 0. It gives the 0. If both switches are closed, then only the current flow, it gives the output. That's why 1 1 is 1 1 1 1, the output is 1. Okay, do you understand? This is switches diagram. Both switches are closed, then only the current flow. That means both yes inputs are high, then only it gives the output. Or if you substitute the formula A dot B, that is 1 into 1 1. Okay students, right? And the next OR gate. OR gate, this is the symbol OR gate. What is the formula? A plus B, input AB, output is C. And see, this is the switching operation. This is the switching diagram. See, if any one switch is closed, what will happen? If any one switch is closed, the current flow, so it gives the output. That's why if both switches are opened, there is no output. That's why 0 0 0. Or if you are substituting the formula 0 plus 0 0. If any one switch is closed, the current flow. Therefore, if any one input is high, definitely it gives the output. So 0 plus 1 1, 1 plus 1 1. Okay students, do you understand? Right. XOR gate. Yes, XOR gate. See this symbol XOR gate. Circuit. See first one. This is which one? NOT gate. See this is which gate? AND gate. So two inputs. One is B, another one is input A bar. Therefore, the output is A dot B. That is A bar into B. The same time is another is AND gate. That is B bar and A. So A into B bar. So both are, these are the input. Therefore, one input is A bar B plus another input is A dot B bar. So this is which gate? OR gate. That's why plus. Therefore, A exclusive B. This is the formula, Boolean algebra formula for XOR gate. A plus A exclusive B. That means A bar dot B plus A dot B bar. Okay, students. Right? If you are substituting the values in this formula, you will get that values. Okay, the output verified with the help of the truth tables. We discussed now, those are all truth tables. The input output verified with the help of what? Truth tables. Okay students, right. Now see this exclusive OR gate. It is XOR gate. I said no, Boolean expression A exclusive B. This is circuit symbol. If you are substitute the formula 0 is 0, the output is 0. That means if you are substituting any one value, A bar is dot B bar plus A into B bar. If you are substitute the values in that formula, you will get this type of which one? Output. Okay students, this is the truth table. What is the formula? A exclusive B. Okay students, right. Next, Boolean algebraic formula. Boolean algebra formula, right? This is some small introduction of Boolean algebra, right? See this? We can interrupt high or low voltage as representing true or false, and a variable whose value can be either 1 or 0, it is called Boolean variable. Which variable? Boolean variable, right? And or not are the basic Boolean operations. What are the basic operations? And or not are the basic Boolean operations, and we can express Boolean functions with either an expression or a truth table, or which one? Truth table, right? And can express Boolean functions with either an expression or a truth table. Okay, students, right? And every Boolean expression can be converted to a circuit, right? And now we'll look at a low sorry how Boolean algebra can help simplify expressions, which in turn will lead to simpler circuits. Okay, so this is a small introduction for Boolean algebra. Okay, students, right? Next, continuation. Recall that two binary values had different names. One is true or false or otherwise on or off, or otherwise yes or no, or 1 or 0. And we use 1 and 0 to denote the two values, right? And there are three basic logic operations. One is and or not, and is denoted by dot, and or is denoted by a plus, and not denoted by an over bar, or yes after the before the variable or after the variable. Okay, students, so and denoted by a dot, that is a dot b, or denoted by a plus, that is a plus b, and not is denoted by an over bar, that is a bar. Okay, students, right? Okay, see this Boolean laws. Yes, these are the Boolean laws. Okay, right? I'll tell you one by one, but see this now. A B which is equal to B A. A B is equal to B A. And see this next one. A plus B is equal to B plus A. Right? Okay. And now come to this one. A plus AB is equal to A. A plus AB is equal to A. And another one is A into A plus B is equal to A. Both are A. Yes. And see the next one. A into B plus C is equal to AB plus BC. And see the next one. A plus BC is equal to A plus B into A plus C. This is dot product and vessel as sum. Now come to this one. A plus B the whole bar is equal to A bar dot B bar. Yes, that's inversion. A dot B the whole bar is equal to A bar plus B bar. Right? Okay. Now come to this one. A into BC is equal to AB into C. Here A plus BC which is equal to A plus B plus C. Right? Now come to this one. A plus A bar B which is equal to A plus B. Next one, A into A bar plus B is equal to AB. So we can prove this output. Okay. Okay, students. Yes. Next, the first one is commutative law. First one is what? Commutative law. See this? That is the formulas. All the formulas has based on these functions. So the first one is commutative law, that one is complement law. First one is complement. See this, suppose if I am taking a, y is equal to a bar, 0 means 0 bar taken as first 1, and 1 taken as 0. So a double bar is equal to a double bar is equal to what? A. Or otherwise if I am taking a, that is equal to what? A bar. That is complement law. Okay students, right. And next R laws. Okay, R law, please see this R law, that is R gate output. A plus B, no, so 0 plus 0 0, 0 plus 1 1, and 1 plus 1 1. Okay, and see the first law, a plus 0, a plus 0, these are the numbers, but see this a plus 0, that is equal to a plus 1 1, a plus a plus a bar is equal to 1. Okay, so these are the R laws. Okay students, right. And next, see I'll tell, I gave no first one, so these are the I separately the last. See the first one is commutative law. Commutative law is nothing but a plus b is equal to b plus a, and a dot b is equal to b dot a. This is which law? Commutative law. And next one is associative law. The associative law is nothing but a plus b plus c which is equal to a plus b plus c. And next is a dot b into b dot c which is equal to a dot b into c. And distributive law, distributive law is nothing but both a sum and dot product will come. That's why see that a into b plus c which is equal to ab plus ac. And see the next one, a plus bc which is equal to a plus b into a plus c. Okay students, right. Okay, so do you know the concept of high and low is not a new one. In fact, it was applied in telephone switching circuits by S. Shannon in 1938. So we already used the zeros and ones in 1938. Okay students, right. See this simple is problem, example problem 9.10. What is the output? What is the output y in the following circuit when all the three inputs a and b and c are first 0 and then 1? So all the inputs first taken as 0 and all the inputs taken as 1. So what is that output, right? Now see this is which gate? AND gate. And this is which gate? NAND gate, right? But see this is the output of the AND gate is input of the NAND gate. So we are taking these values and input C. So A 0, B 0 and C 0. So A 0 0. Yes, the X is what? A dot B formula. AND gate formula is A dot B. So the output X is 0. And that input is, yes, X is 0. Therefore X is what? 0 into C, the whole bar taken as 1. And if the taking as all the inputs are high, 1, A1, B1, C1. So if it is A1 into 1, what will come? 1. Yes, so X is 1. If I am taking that this is the input, therefore what is the formula for NAND gate? A dot B into, A dot B whole bar. So therefore A is X dot c whole bar, so that is inverse, therefore 0. Okay students, right? Okay, next De Morgan's theorem, right? The De Morgan's theorem, there are two theorems, there are two theorems, right? There are two theorems in that Boolean algebra sections. One is De Morgan's first theorem, another one is De Morgan's second theorem. The De Morgan first theorem state that the complement of the sum of two logic inputs is equal to the product of its complements. So please note it down students. The first theorem state that the complement of the sum of two logical inputs is equal to the product of its complements. Okay students, this is a theorem. We can prove the theorem. Proof, see this. The Boolean equation for NOR gate is A plus B the whole bar, right? The Boolean equation for is bubbled AND gate is sorry, the Boolean equation for bubbled AND gate is y is equal to A bar dot B bar, right? So what is the theorem? The sum of the two logic inputs is equal to product of its complement. So complement of the sum is equal to product of its complement. So both cases generate same output for the same input. It can be verified using following truth table. So with the help of truth table we can verify the outputs, right? See, this is first one, 0 0. Yes, so this is that output verifying. See this, a plus b the whole bar, complement of the sum is equal to product of the complement. That's why I'm split up a plus b, a bar b bar, a bar dot b bar. Okay, what is the input? 0 0. So 0 plus 0 0. This is a plus b. You take an inverse, 0 inverse 1, right? Now come to this a bar. So come to the input. This is 0. We are taking inverse 1, and next is b bar. B is 0. We are taking as inverse 1. Next a bar dot b bar. So what will come? Already a bar is there, b bar is there. That you have to dot product. So 1 into 1 1. The same way if you go to this one, 0 plus 1 1. You will taking inverse a plus b the whole bar 0, and a inverse is 1 and b inverse 0. A inverse dot, that is a bar dot b bar is equal to 0. So 1 into 0 0, right? If the same way if you go to this side, a plus b, so 1 plus 0 1. So a plus b the whole bar, we are taking a plus b the inverse, you will get 0, and a bar here 1 inverse 0, and b bar 0, so we are taking bar 1 here. Next a bar dot b bar, so a bar is there, b bar is there, therefore 0 into 1 0. The same way come to this side, a plus b, 1 plus 1 1, and taking inverse a plus b the whole bar 0, a bar 0, b bar 0. Yes, and here a bar dot b bar, so 0 plus 0 0. The same way we are taking output. Okay students, right? Next theorem, second theorem. The second theorem state that the complement of the product of two inputs is equal to the sum of its complement. Which complement? Sum of its complement. Okay students, so complement of the product is equal to sum of its complement. This is the theorem. So see this, the Boolean equation for NAND gate is A dot B the whole bar. Product of complement is equal to sum of its complement, that is A bar plus B bar. Okay students, right. So see that we can verify the truth table. Here a split up A B, A dot B, A dot B the whole bar, A bar, B bar. Here A bar plus B bar. See this 0 into 0, 0. A plus B the whole bar, taking inverse, you will get a 1. And A bar, this is 0, therefore 1. And B is 0, we are taking inverse 1. So here A bar plus B bar, so 1 plus 1, 1. The same way, see this 0, 1. So A dot B 0. And taking inverse A dot B the whole bar 1. Here A bar 1 and B bar 0. We are taking plus A bar plus B bar, 1 plus 0, 1. Now come to this one, 1 0 input. So A dot B 1 into 0, 0, and taking inverse A dot B the whole bar taken as 1. And here A bar is 0 and B bar is 1. See, we are taking input from this side. And here A bar plus B bar. See the next value, 0 plus 1, 1. Now come to this one, A, B, 1, 1. So 1 plus 1. So 1 into 1, A dot B, 1. We are taking inverse. So 1, we are taking inverse 0. That is A dot B the whole bar. And if we go to this side, A bar, already A is 1. So if we are taking bar 0. And B is 1, taking inverse 0. So here next A plus B, that is A bar plus B bar. So here already A bar is there, B bar is there. Therefore 0 plus 0, you will get 0. So this is the truth table for second theorem. Okay students, right? You understand? Okay. You see that yes, based on that formula Boolean identity, simplify the Boolean identity. What is Boolean identity? See this, AC plus ABC is equal to AC. We can prove. So we can use the OR laws, AND laws and NOT laws. Okay. First we have is simplify this one. See here A is there, here also A is there. So AC is there. So AC taken is outside now. So AC taken as outside, what will come? 1 plus B is come. So that means 1 plus B, that is equal to 1 plus A. So what is 1 plus A? 1 plus A is equal to 1. Yes, using OR law, second law, 1 plus A is equal to 1. Therefore, AC into 1, what will come? AC. That is A into 1, A. That's why AC into 1, AC. Therefore, AC plus ABC is equal to AC. That is proved. So, yes, for this output, I draw the diagram. Yes. So, AB is NOT gate. The output is AC. And ABC is the another, AND gate. The output is ABC. So, both are combined in which product? Plus, therefore, OR gate. So AC is one input, ABC is the another input. So what is the formula? What is the output? This is OR gate now, that's why plus. Therefore AC plus ABC, therefore it gives the output AC. That is equal to which gate? AND gate. That is equal to which gate? AND gate. Okay students, right? So De Morgan's theorems are very very important question, 5 mark. Okay, and Boolean and algebra, that formula is also very very important. That is OR law, AND law, NOT law. Okay, and the last is very very important, 3 mark questions. Okay students, right? Okay students, right. Thank you students. today class is over. Okay students, we'll see on next video students. Thank you. Sorry, one formula is missing. See this example problem. Yes, that's why I'll take this one. See this, in the combination of the following gates, write the Boolean equation for output y in terms of input a and b. See, a is input of AND gate and b is also input of AND gate but attached to the NOT gate. So the input of AND gate here b bar is a fraction of input is fed to another AND gate and attached to the NOT gate, and b input is connected to which one? AND gate. So here a, the input is b bar here, but here a bar and b, so it is both output is connected to the input of OR gate. Now what is the output, right? So it is easy to find out the output of the first AND gate. See this, I said no, a into b bar, and this one a bar and b. So what is the output? OR gate. So plus, therefore we have to sum. So a dot b bar plus a bar b. So that is which gate? Which is equal to XOR gate. The output y is equal to a dot b bar plus a bar dot b bar. Okay students, right? Okay, so all the example problems are over. Okay students, will you see on next video. Thank you students.